Okay, hello everyone. We should be live. We'll wait a few more minutes to see if anyone else joins. Okay, let's begin. Alright, so today's lecture will be on greatest common divisors and least common multiples, and my name is Perrin Chang. If you have any questions, just feel free to type it in the chat. Alright, so let's start with some few basic notations and definitions. So if we say this notation A bar B means that A divides B, or A is a divisor of B, and this also means that B is the multiple of A. A common divisor of a group of numbers is any integer d that divides all the numbers. So for example, if we have the numbers a1, a2, a3, and so on, the common divisor of all of them is that any integer d such that d divides a1, a2, and d divides all the numbers. So the greatest common divisor out of all these numbers is the greatest of all possible d. This is typically denoted as the GCD, and then within parentheses, what we want the greatest common divisor of all those numbers to be. A common multiple is a multiple. Similarly, common multiple is a multiple of all the numbers. That's all multiple of all the numbers, and the least common multiple is the least of all the common multiples of set of numbers that we want. So we say that two numbers are relatively prime if they do not share any prime factors. For example, the numbers 9 and 25 are relatively prime. Notice that both the 9 and 25 do not have to be prime numbers, but since they don't share any prime factors, they're relatively prime. So the next two are pretty self-explanatory, they're pretty intuitive. So the minimum you use this notation to denote the minimum of a set of numbers, and max to denote the maximum of a set of numbers. Okay. Next slide. So the prime factorization of an integer is when you express the number as a product of primes. So typically, this is written in the form a prime to a power. So instead of writing the primes all multiplied together, we can use the power notation. So as an example, we can find the prime factorization of 612. So we see that 612 is divisible by 2 since it's even. So we know that 612 is equal to 2 times something. If you divide 612 by 2, you get that it is equal to 2 times 306. And notice that 306 is even as well, so that is divisible by 2. So 306 is equal to 2 times 153. And then you notice that 153 is divisible by 3, since the sum of its digits is a multiple of 3. And if you divide 153 by 3, you get that it is equal to 51. And then similarly, 51 has a digit sum that is equal to 6. So it is divisible by 3 again. If we divide 51 by 3, then it is equal to 3 times 17. Hence, we can express 612 as 2 times 2 times 3 times 3 times 17. However, since we have two factors of 2 and two factors of 3, we can use the power notation. Well, yeah, so it would be 2 squared times 3 squared times 17. And this will be the prime factorization of 612. Basically, what you're doing is writing 612 as a product of prime numbers, which you can see is what I demonstrated below. So here are two properties of divisors. If A divides B and B divides C, then A divides C. So this is basically saying that the property of divisor is transitive. Another property is that if an integer n divides both A and B, it divides the sum of these numbers and the difference of these numbers. So we can prove it by just noting that since n divides A, we can write np equals A for some integer p. We don't know what p is, but we just know that n multiplied by integer p, an integer can equal A. And similarly, n times q equals b. And now if we add A and B, we get that n times p plus q equals A plus B. So this means that since n is being multiplied by an integer and n equals A plus B, then n divides A plus B. And in a similar fashion, if we subtract these, then we get n times p minus q equals A minus B. So n divides A minus B, since n is being multiplied by b by integer, and we get A minus B as a result. So in the next slide, we'll show how to find the greatest common divisor. Remember that the greatest common divisor is basically the greatest of all the common divisors. So the first thing you want to do is prime factorize both numbers, and then for each prime, you want to take the between A and B. You want to take the lowest exponent. So this is rather confusing, so we'll demonstrate with an example. So we're asked to find the greatest common divisor of 36 and 48. So we can first start by prime factorizing it. So realize that 36 equals 4 times 9, which is then 4 is equal to 2 squared, and 9 is equal to 3 squared. So since 2 and 3 are primes, it's the prime factorization of 36. Similarly, we can prime factorize 48. Notice that is equal to 6 times 8. And 6 is equal to 2 times 3, and 8 is equal to 2 cubed, sorry. And if you just simplify this, it is equal to 2 to the 4th times 3. And we consider the primes individually. So for 2, we're going to consider prime 2 first. Since 2, we've prime factorized it, and we want to find the lower exponent between the 2, and 4. Since the lower exponent obviously is 2, the power of 2 and its prime factorized in the greatest common divisor of 36 and 48 must be 2 to the 2 squared. So the greatest common divisor must have 2 squared. And similarly, between 3 squared and 3, the lower exponent is 3 to the power of 1. So the greatest common divisor of 36 and 48, when considering considering 3, it's going to be 3 to the power of 1. And now this is simply the greatest common divisor of 36 and 48, which we can evaluate that this equals 12. Well, the other thing to consider is that since in this problem we only had 2s and 3s, but if, for instance, we had a 5 in here somewhere, since, for example, 2 to the power of 4 times 3 times 5, then we can, in the first number, we can view it as 5 to the power of 0, which is equal to 1. So we'll just take the power of 0 instead. Yeah, because we can just imagine as bunch of primes. For example, we can imagine as 5 to the power of 0 times 7 to the power of 0, and so on. We'll still consider these since they're all times 1. And if you want to, and algebraically, this is evaluated as this. It's kind of confusing, so you might just want to, you should understand it, but you don't need to directly memorize it. Okay, now for the second problem, we're asked to find the greatest common divisor of 7 to the power of 6 times 5 to the power of 4 times 2, and 7 to the power of 3 times 5 times 3 squared. If you have any thoughts, just type it in the chat. I'll give you a few minutes to think about it. And again, if you have any ideas, you can just type it in the chat. Okay, so let's come back to the problem. So remember that this isn't really much different from the previous problem, except that we've already been given the prime factorization. So we can consider the first consider the prime 2. In the first number, it's 2 to the power of 1, and in the second number, it's 2 to the power of 0. So the lower exponent is obviously going to be 0. So 2 to the power of 0 is in our prime factorization of the GCD of these two numbers. And now we can consider the next prime, which would be 3. And in the first number, it's 3 to the power of 0. And in the second number, it's 3 to the power of 2. So obviously it's going to be 3 to the power of 0, since the 0 is less than 2. And now for the next prime, which is 5. In the first number, it's 5 to the power of 4, and in the second number, it's 5 to the power of 1. Since 1 is less than 4, the prime in the GCD of these two numbers is going to be 5 to the power of 1. And the next prime is going to be 7. Similarly, since 3 is less than 6, then the prime factorization of the GCD of these two numbers, it's going to be 7 to the power of 3. Since we've used all these primes in these numbers, this is just going to we have this number, which is going to be the greatest common divisor of these two numbers. Since it's rather large, I'm not going to evaluate it, and I'll just leave it in the prime factorized form. Alright, so in the next slide, we'll demonstrate how to find the least common multiple. So in the greatest common divisor, what we did is we first prime factorized it, and for each prime, we consider the lower exponent. But to find the least common multiple, we do the opposite. We find the greatest exponent between the two numbers. So again, let's do it with an example. So we're asked to find the least common multiple of 12 and 15. I'm going to first prime factorize this thing. So 12 is divisible by 4, so that'll be 2 squared. And it's also divisible by 3. If we check this, we get that 3 times 2 times 2 does equal 12. And 15 equals 3 times 5. Now, if we first consider the prime 2. In 15, the exponent of 2 is 0, and it's omitted, so this equals 1. So we take the greatest number, which is going to be 2. Then we consider the prime 3. In both numbers, it's 3 to the power of 1, so we just take either one. It doesn't really matter. And then we consider the prime 5 next. In 12, it's 5 to the power of 0. Or in 15, it's 5 to the power of 1. So, since we've considered all the primes, this is the least common multiple of 12 and 15. Essentially what we did is for each prime we considered, well, we take the greatest exponent between the two numbers. And here's the next problem. We're asked to find the least common multiple of 24 and 16. If you have any ideas, just set it in the chat. I'll give you a few minutes. Is it 48? Yeah, it is 48. If you want to if you want to write how you figure that out, you can feel free to say that as well. Okay, so for some people, it'd be rather obvious that it is 48, like just by number sense. But since we're learning how to do this, let's use our method with prime factorization. So let's first prime factorize 24. You see that is 8 times 3, and 8 is 2 to the 3, 2/3 power, and then we have a factor of 3. And 16 is simply 2 to the power of 4. And we first consider the prime 2. In 24, it's 2 to the power of 3, and 16 is 2 to the power of 4. We're in the larger exponent, so we want 2 to the power of 4, and it's the least common multiple of 24 and 16. Next, we consider the number 3, the prime 3. In 24, it's 2 to the power of 1, while in 16, it's 3 to the power of 0. So we want the greatest one, so it would be 3 to the power of 1. If we want to evaluate this, this will equals 48. which is our final answer. Okay, here are a few properties of greatest common divisors and least common multiples. The first one is really important. You might want to write this down or at least try to remember it. So if you multiply the greatest common divisor and the least common multiple of two numbers, it equals the product of the two numbers. Since remember when we found the greatest common divisor, we took for each prime we took the lower exponent, and for the least common multiple we took the greater exponent. Since the lower exponent must come from one number, and the higher exponent must come from the other number. If you just multiply the greatest common divisor and least common multiple, what you're actually doing is just multiplying the two numbers. So we're going to just do an example. So for example, the greatest common divisor of 6 and let's see, 781. I just made that number up. I don't know what that. I don't really know too much about it. And the least common multiple of 6 and 781. Since the greatest common divisor times the least common multiple is just the product of these two numbers, which equals 6 times 781. Since it's such a large number, I'm not going to evaluate it. I'll just leave it in this form. If you don't understand the concept, the reasoning behind it, you can just read the transcript after class. So I think this explanation explains it pretty well. And you can also ask it on our Discord server. And the second property is that every common divisor of A and B divides the greatest common divisor of A and B. So if the greatest common divisor of A and B is in D, and C divides A, C divides B, and C divides D. Basically what this is saying is that notice that C is a divisor of both A and B. So it's a common divisor of A and B. Notice that D is the greatest common divisor of A and B. So C, based on the first sentence, you know that C divides D. And similarly, any multiple of A and B any common multiple of A and B must be a multiple of the least common multiple of A and B. So let's go to an example. So we're asked to find the product and the product of the greatest common divisor and least common multiple of 18 and 42. So recall that from our first identity on this slide, we have that the greatest common divisor of two numbers times the least common multiple of two numbers equals the product of the two numbers. So we get that the greatest common divisor of 18 and 42 times the least common multiple of 18 and 42 equals 18 times 42. Since the left side is just basically what we want, we just simplify the right side. Multiplying 18 and 42, we find that is equal to 756. So the greatest common divisor times the least common multiple of 18 and 42 is equal to 756, which is the product of 18 and 42. And a second example, if you have any ideas, you can just type it in the chat. I'll put this out as an exercise. Okay, 70. Yeah, good job. It is 70. Yeah. So if you also want to explain how you got it, you can type it down as well. Yeah, but it's the right answers. Good job. I'll also give a few more minutes if anyone else wants to think about it. Okay, let's work with the problem now. So unless someone's really familiar with numbers, then it'd be quite difficult to immediately find the value of n without using some of the properties we have. So again, recall that the greatest common divisor of two numbers times the least common multiple of two numbers equals the product of two numbers. So we have that GCD is 40 times the LCM of n and 40 equals 40n. But recall that we're given the GCD of n and 40 and the LCM of n and 40. We're given that the GCD of n and 40 is 10 and the LCM of n and 40 is 280. Remember that 10 times 280 is 40n. So now we have this equation, so we can solve for n. If you simplify the left side and divide by 40, you'll find that n is equal to 70, which is our final answer. So our next topic is the Euclidean algorithm, which gives us a rather powerful and quick way to find the greatest common divisor of two numbers. So it's rather complicated to demonstrate by lots of words. So I'm going to show this by an example. So first of all, recall that if D divides A and B, it must divide A minus B. So I'll show this with an example. So I'll first establish a fact, or like a lemma if you want to call it. So I want to show that the greatest common divisor of A and B equals the greatest common divisor of A minus B and B. Okay, so that's what I want to show. So we can let the GCD of equals D and the GCD of A minus B equals D prime. So what I want to show is that D equals D prime. So from the first equation, we can establish that D divides B and D divides A. Since D divides both B and A, it must divide A minus B. In a similar fashion, D prime divides A minus B, and D prime divides B. Now, before I demonstrate the proof, if anyone has an idea of how the proof should continue, you can just type it below. I'll give you a few minutes. Okay, it's been a few minutes, so I'll come finish the proof. So since we have, let's work with the first equation. So since d divides b, and d divides a minus b, I know that d is a common divisor of b and a minus b. This means since d is a common divisor of these two numbers, d must divide the greatest common divisor of these two numbers. However, remember that we defined the greatest common divisor of a minus b and b to be d prime. So d just divides d prime. And now let's work with the second equation. Since d divides a minus b and d divides b, it must divide, d prime must divide its sum, which means that d prime divides a minus b plus b, which is simply a. Now, since d prime is a common divisor of b and a, d prime must divide the greatest common divisor of a and b, which turns out that is d, since we define it to be d. Now, since d divides d prime and d prime divides d, this shows that d prime equals d. And therefore, since d prime equals d, and d equals the left-hand side of the original equation, and d prime equals the right-hand side of the original equation, we've shown that the greatest common divisor of a and b equals the greatest common divisor of a minus b and b. Now, this is an incredibly powerful part that we can use to complete the Euclidean algorithm. So let's say we have two numbers, and we're asked to find the GCD of 90 and 12. Since these are rather small numbers, you'll probably use our normal way, and you'll get the answer too. But since with the GCD of 90 and 12, it's also equal to the GCD of 90 minus 12 and 12, which equals the GCD of 90 minus 12, which equals to 78 and 12. So basically what this allows us to do is to subtract numbers. But rather than subtract 12 each time, what we can do is subtract 90 subtracted by a multiple of 12. So what we can get, so notice that 12 times 7 equals 84. So we can subtract 84 from the left side. Since if you don't subtract 84, instead we subtract 12 times 6 is 72. We'll get is 8. The GCD goes to 18, 12, and 8 and 12. And then we subtract 12 equals the GCD of 6 and 12, which now one can easily evaluate that this is equal to 6. And let's say, what if we don't immediately see the GCD of 6 and 12 is equal to 6? Well, we can apply it again, but this time, instead of subtracting the right number from the left number, we subtract the left number from the right number, which just this then is GCD 6 minus 12 is equal to 6, 6 and 6, which now obviously is 6 because they're the same number. So basically what we're able to do is to use the remainder when the larger number is divided by the smaller number and replace the larger number with the remainder. And then you can keep doing that until you reach a number that is easy to find the greatest, reach two numbers that's rather easy to find the greatest common divisor of, such as, for instance, in 6 and 6. There's obviously the greatest common divisor of these two numbers is 6, since they're the same number. So let's go into an example. Although you can find more information about it online. We just gave in this lecture, we just gave a rather basic demonstration of it. So this problem asks us to find the greatest common divisor of 9,351 and 27. So obviously we can use the Euclidean algorithm and subtract 27 from 9,351. But we don't want to subtract it one by one. You can subtract it by a multiple of 27. And what we can do is we can divide 9,351 times 27, which we get that 9,351 equals 27 times 346, plus 9. So if we subtract 27 times 346, since we're just subtracting 27 each time, so basically what this is doing is subtracting 27 346 times. This equals the GCD, and then left with a remainder of 927. Obviously, one can evaluate this as 9 if you see it immediately, but we can also subtract 9 3 times, or 2 times if you want to. It doesn't really matter. At this point, it's pretty obvious. 9 and 8, 9 and 9. We get that the GCD is obviously 9. So our final answer is 9. Notice how much quicker this was than prime factorizing 9,351. Okay, for our next problem, I'll give you a few minutes to think about it. If you have any ideas, you can put it in the chat. It's just one, yeah. It's just one, yeah. Yeah, good job. It's just one, yeah. So as Heather Feathers 2 pointed out, the answer is just one, which is the Euclidean algorithm. You get that the GCD of these two numbers equals we divide 3523 by 15 equals 15 times 234 plus 13. So using the Euclidean algorithm, we just want the remainder. So this is equal to the GCD of 13 and 15. And since 13 and 15 are relatively prime, our GCD is just 0 to 1. Final answer. So here are a few more examples. These are probably more challenging than the problems that we've gone through. So if you have any questions, please type it out. And yeah, just please ask questions if you don't understand anything. Okay, I'll give you a few moments. If you have any ideas or answers, you can just type it in the chat. Okay, so let's begin the problem. So we're asked to find the smallest possible integer that leaves a remainder of 1 when divided by numbers 2 through 9. So when n leaves a remainder of 1 when divided by these numbers, so realize that n minus 1 leaves a remainder of 0 when divided by the numbers 2 through 9. So 2, 3, all the way to 9, these numbers, they all divide n minus 1. Remember that we're letting n equals the number we're looking for, right? Since n is a remainder of 1 when divided by all these numbers. So these numbers all divide, or they're all divided to n minus 1. So this problem is essentially asking us to find the least common multiple of these numbers. If we make the substitution n minus 1 equals m, this problem becomes 2, 3, and all the way to 9 divides m. So now we can just find the least common multiple of the numbers 2, 3, all the way to 9. We first prime factorize them. So these are the numbers, and we want to find the least common multiple. Let's consider the prime 2 first. The greatest power of exponent of power that occurs is 2 squared. So the least common multiple is 2 squared, has the factor of 2 squared. And for 3, the highest exponent is 3 squared. And for 5, it's just 5. And for the next prime 7, we'll have 1 7 that appears. And if we simplify that, this number should be equal to 2,520. So, since this is the least common multiple of the numbers 2 through 9, every common multiple of the numbers 2 through 9 must be a multiple of 2,520. Since we're asked to find the smallest number, we can let this number 2,520 equal m. And since we're asked to find n, we'll simply add 1 to m. We'll get that our n equals 2,521, which leaves a remainder of 1 when divided by the numbers 2 through 9. Is our final answer, 2,521. Oh yeah, sorry, yes, 2 is 8. Yeah, it is 2 cubed, my bad. Yes, you're right. Yeah, it is 2 cubed. Sorry about that. Yeah. So yeah, 2 cubed times 3 squared times 5 times 7 equals 2,520. Yeah, if you have any questions on my explanation, you just leave it in the chat, and then I'll try to explain it as best as possible. Okay, for the next problem, it's from the AMC competition. If you have any ideas, you can again just send in the chat. I'll give you a few moments. Think about it. Okay, let's begin. Yeah, so this problem is probably most challenging on our lecture today. So so if you have any question, just ask any question if you have any questions on my explanation. So we're given that the greatest common divisor of A and B is 24, the greatest common divisor of B and C is 36, the greatest common divisor of C and D is 54, and the greatest common divisor of D and A is between 70 and 100. We're also asked, this is a multiple choice question, we're asked which of the following must be a divisor of A. So there are many fake ways to solve this problem, but those aren't really instructive, so we're going to try to solve this in a proper way. So what we want to do is find the greatest common divisor of D and A, let's focus on finding the greatest common divisor of D and A. So from the first equation, we notice that the greatest common divisor of A and B is 24, which immediately means that A must be a multiple of 24. So I can write that A is a multiple of, and it's better if you prime factorize it so we can see it as factors. 2 to the 3 times 3. And from our last equation, you can see that D is a multiple of 54. So D multiple of 54, if I'm prime factorize it, you see that is 2 and 3 to the power of 3. And so the greatest common divisor, if we consider the factor of 2 first, of D and A, must be at least 1 power of 2. Since D is a multiple of has 1 power of 2 in it, at least. And what we want to ask ourselves is, in the greatest common divisor of D and A, is 2 to the power of 1, or can it be a power of 2, or something else? But from our second equation, we see that the greatest common divisor of B and C is 36, which means that C is a multiple of 36, which is 2 squared times 3 squared. And we also know that the greatest common divisor of C and D is 54. So since C is a multiple of 4, if D was also a multiple of 4, that means the greatest common divisor of C and D could not only have 1 power of 2. It would have to have at least 2 powers of 2. So that means D only has 1 power of 2 in it. And as a result, the greatest common divisor of A and D only has 1 power of 2 in it. So you got that the greatest common divisor of D and A has only 1 power of 2. And now, since this kind of solves half the problem, since we've worked with 2 already, let's work with 3. We're going to apply a similar idea. So since A is a multiple of 3 and D is a multiple of 3 cubed, we can also see from our second equation that B is a multiple of 9. Multiple of 36, which is a multiple of 9. So since so we want to ask ourselves here, can the prime factorization of the GCD of D and A have 1 power of 3 or 2 powers of 3, or so on? If but in a similar fashion to how we found that 2 can only have 1 power of 2, the GCD of D and A, we can only have 1 power of 3. Does everyone see that? Right? And now we're also given that the GCD of D and A is between 70 and 100. So since we can't have any more 2s and 3s in the prime factorization of the GCD of D and A, we have to find another number that's in the to get between 70 and 100. So the GCD of DNA is equal to 6 times n, something n, where n does not have any 2s or 3s in it. So if you want to test it, we can find that 7, 6 times 7, I guess it's 42. That's not going to work. And then going to 11, 6 times 11 is 66. That's still too small. However, 6 times 13 works. So we can let the GCD of GCD of DNA must be 6 times 13, which equals 78. And since A must be a multiple of 78, it must be a multiple of 6 and 13. So our final answer is D, 13. Right? Also notice that 17 does not work since it's too big. 17 times 6 gets us a number that's greater than 100. Okay, here's our final problem for today's lecture. I'll give you a few moments as well to read the problem. Um, 33, yeah, the answer is 33. Yeah, good job. Um, yeah, so let's go into how the problem is solved. So Alex starts counting by sixes from 6. So basically what Alex is doing is he's counting all the multiples of 6 that are 400 or less. And Matthew is doing something similar. He's counting all the multiples of 4 that are 400 or less. So Alex is counting all the numbers in the form 6n, where n is an integer, positive integer. And Matthew is counting all the numbers that are in the form 4m. Well, m is an integer, is a positive integer. So in order, since Alex is counting all the multiples of 6 and Matthew is counting all the multiples of 4, they count all the numbers that are multiples of the least common multiple of 6 and 4. So this problem is essentially asking us how many numbers that are multiples of the least common multiple of 4 and 6 are less than 400. So we can first calculate the least common multiple of 4 and 6, which you can calculate by inspection, which is equal to 12. Least common multiple of 4 and 6 is equal to 12. So since any common multiple of 4 and 6 must be a multiple of the least common multiple, all the numbers counted by both Alex and Matthew will be a multiple of 12. So the numbers counted by both Alex and Matthew is in the form 12p, where p is a positive integer. So now all we have to do is find how many multiples of 12 are less than 400. So we gotta find out 12 times 1 is equal to 12. And then we just go so on. If you divide 400 by 12, you'll find that 400 is equal to 12 times 33 plus 4. So numbers that will count will go all the way up to 12 times 33, which equals to 396. So there are 33 numbers that are counted by both Alex and Matthew. 12 times 1, 12 times 2, all the way to 12 times 33. So our final answer is 33. And that concludes today's lecture. If you have any questions, you can still leave it in the chat. So be sure to check out our website and our Discord server where we'll be posting a problem set so you can practice your problem solving skills. Everything is linked in our bio. You can check out our YouTube, our website, our Instagram, and our Discord. Particularly our Discord is probably the most important, which you can receive updates. Yeah, if you don't have any questions, I'll end the stream. And yeah, have a good one. Yep, thanks for joining. Also, if you follow our channel, then every time we have a new stream, you'll receive a notification. So that's really beneficial. Okay, bye guys.